When a beam of light traveling through empty space strikes a transparent material, it hits a physical boundary that slows and pivots its trajectory sharply. While light travels at a constant speed in a vacuum, its pace changes the moment it enters a physical medium. We see this speed reduction occur anytime light passes into everyday transparent materials, like a pane of glass or a pool of water. This specific change in direction, caused by a change in speed across a boundary, is called refraction. This animation illustrates the physical pivot. When a wide wave of light hits a material at an angle, one edge of the wave enters and slows down fractions of a second before the other side. The faster side overtakes the slower edge, dragging the entire wave into a new angle. This pivot is continuous until the entire width of the wave has crossed the threshold and is fully submerged in the new material. This geometry is why a straw appears broken or physically shifted when you place it in a glass of water. Mastering optics requires measuring the geometry of this bend to predict exactly where the light will go. This measurement leads to a specific question: what happens if we push this geometric bending to its physical limit? By tracking this geometry, we will discover a mathematical threshold where light ceases to pass through the boundary and becomes trapped inside the material. This schematic shows a semicircular glass block, the standard laboratory tool used to isolate and measure how light bends. The curved bottom edge allows light to enter exactly perpendicular to the surface, without bending. This isolates all the refraction to a single event at the flat top boundary, where the light exits into the air. To measure this event, we must draw a perpendicular dashed line exactly where the light strikes the flat boundary. This line is called the normal. It serves as a reference, pointing straight out of the surface at precisely 90 degrees. Every single angle is measured between the light ray and the normal, rather than from the glass surface itself. Watch the light ray as it enters the glass and travels toward the flat top boundary. The angle between this arriving ray and the normal is defined as the angle of incidence, denoted by the letter I. As the light ray exits the glass and speeds up in the air, it refracts, bending away from the normal. The angle between this exiting ray and the normal is defined as the angle of refraction, denoted by the letter R. The relationship between these two angles is linked by a specific value called the refractive index, denoted by the letter N. This equation demonstrates that the refractive index equals the sine of the angle of incidence divided by the sine of the angle of refraction. The refractive index is essentially a material's unique speed limit rating. It mathematically dictates how aggressively that specific material will bend light. Returning to the laboratory experiment, we can stress test this math by sweeping the light source to gradually increase the angle of incidence. This first diagram shows the immediate result. As the incident angle grows wider inside the glass, the refracted angle in the air grows even wider. Because the exiting light is bending away from the normal, it is being pushed closer to the flat surface of the glass block. We pause the experiment at the exact moment the refracted ray stops traveling upwards. As this second diagram illustrates, the ray now skims flat along the surface of the block, making the angle of refraction exactly 90 degrees. This specific tipping point is called the critical angle, denoted by the letter C. The critical angle is the maximum angle of incidence for which refraction can still occur. Because the angle of refraction is locked at exactly 90 degrees at this threshold, the previous refraction equation simplifies. This formula establishes the rule for the threshold. The sine of the critical angle equals 1 divided by the material's refractive index. For a glass block with a refractive index of 1.5, we calculate the inverse sine of 1 over 1.5 to find our threshold. For this specific piece of glass, 41.8 degrees is the mathematical limit for light to behave as a wave escaping a boundary. If 41.8 degrees is the limit, what physically happens if we push the laser to 43 degrees? Looking at this third diagram, the beam skimming the surface disappears entirely. Instead, a new beam abruptly reflects downwards, back into the glass. This phenomenon is known as total internal reflection. Total internal reflection demands two strict conditions. First, light must be attempting to move from a denser medium, like glass, to a less dense medium, like air. Second, the angle of incidence must be greater than the critical angle. Once trapped, the light abandons the complex math of refraction. It obeys the simple law of reflection, where the angle of incidence exactly matches the angle of reflection. Exceeding the critical angle changes the physics of the material, turning a transparent window into an inescapable mirror. This diagram illustrates a primary application of total internal reflection, the optical fiber. It relies on an inner cylinder, the core, made from dense glass with a high refractive index. The outer cladding has a strictly lower refractive index. This design fulfills the first condition of total internal reflection, light traveling from a denser medium toward a less dense medium. A laser signal is fired into the core. It strikes the walls at a shallow angle. Measured from the normal, this angle exceeds the critical threshold, fulfilling the second condition. The light perfectly reflects, causing a continuous ricochet down the fiber. Because of total internal reflection, no light refracts into the cladding. 100% of the signal is retained as it travels over vast distances. Mastering the geometry of a single bouncing light ray is the foundational physics that allows the internet to travel across oceans at the speed of light.